Welcome to this Astronomy in the City presentation. Space, spins, and very dense things, the whirling wobbliness of processing gravitational waves. By me, Lucy Thomas, a PhD student at the University of Birmingham's Institute for Gravitational Wave Astronomy. Pretty much everything in the universe is rotating. Once an object has started spinning in space, due to the vacuum of space and lack of frictional force, it generally doesn't stop. Let's think about all the different rotations that we're doing right now. Firstly, we know that the Earth rotates on its own axis once every 24 hours, and this makes day and night happen. We also know that the Earth is orbiting around the Sun, approximately once every 365 days, and this creates our yearly cycle. Not only that, the solar system resides within the disk of the Milky Way galaxy, and this galactic disk is also rotating, with the solar system completing one full revolution approximately once every 240 million years. But these rotations are rarely constant forever. As objects are moving and rotating, other objects come closer and move further away. Therefore, the gravitational forces acting upon the original object are constantly changing. This will tend to gradually change their rotational motion. In astronomy, we use the word precession to describe the slow change in the rotation of a spinning body. But as there are different kinds of rotations, there are also different kinds of precession. I am going to briefly describe the two kinds of precession which are most relevant to Earth and our solar system. The first is perihelium procession. This refers to the fact that the planets generally do not trace out the same ellipse every time they go around the Sun. The shape slowly changes so that the consecutive orbits look like the petals of a flower. This effect is mainly due to the gravitational forces exerted by other planets in the solar system. The second is axial procession. The Earth undergoes axial procession as the axis upon which it rotates moves very slowly in a cone shape. This happens because the Earth is not actually a perfect sphere, but bulges slightly at the equator. Therefore, the Moon and Sun exert stronger tidal forces on the equator than the poles, which gradually changes the orientation of the Earth's rotation axis. It is thought that this axial precession has been a key factor in prehistoric ice ages. But in astronomical terms, the Earth and other planets are very small and move very slowly. So what about the precession of heavier objects moving a lot faster? We will come back to this idea of precession later in the talk. But for now, we're going to take a slight detour and talk about gravitational waves. The detection of gravitational waves has provided a new window onto the universe, allowing us to view phenomena which can't be seen with other kinds of astronomy. A key source for ground-based gravitational wave detectors, and the only type of source we've detected thus far, is the merger of binary black holes and neutron stars. The LIGO-Virgo collaboration has so far published 50 detections from merger events like these, with the vast majority being binary black hole mergers, but also 2 binary neutron star mergers as well. For the remainder of this presentation, we will be focusing on binary black hole mergers. The figure on the left shows what the typical gravitational wave signal from a binary black hole merger might look like, with a visual representation of what the binary might look like at the top. We can split the gravitational wave signal into 3 regions: the in-spiral, the merger, and the ring-down. A gravitational waveform can also be split into different parts, which we call modes. The more complicated the motion of the binary as it in-spirals towards merger, the more modes are needed to fully describe that gravitational wave. According to the no-hair theorem of black holes, a single black hole can be completely described by just 3 things. Firstly, its mass, a single number which tells you how heavy the black hole is in solar masses. Secondly, its spin, a 3D vector which tells you the axis of rotation around which the black hole rotates. Thirdly, its electric charge, although for our purposes, we will be hereafter assuming that all of our black holes have no charge. And we also need to know where in the sky the black hole is, its distance, and the 2 angles to tell us the sky location, right ascension and declination. That makes a total of 5 parameters that we have to consider for a single black hole. But what about for a gravitational wave, which involves 2 black holes? The shape of a particular gravitational waveform from a binary black hole source depends on the source parameters. So when we detect a gravitational wave signal, its source parameters are encoded into the gravitational wave and need to be teased out. In order to do this, we need waveform models to compare to our detected signal. We have banks of pre-computed waveforms with known parameters, so that when a gravitational wave signal comes into the detectors, we can deduce the source parameters based on the best matching waveform template. We need these models to be very accurate so that we can deduce the source parameters correctly. They also need to be fast because one parameter estimation process usually requires millions or even billions of waveform model evaluations. And lastly, they need to include all the relevant physical phenomena that we might expect to see as part of a binary black hole merger. As an example of how the source parameters encode themselves into the gravitational wave signal, consider this picture again. The further away the black hole merger happens, the weaker you might expect the gravitational wave signal to be, because the same energy is being spread over a much larger volume. And this is true. So the distance to the source is imprinted in the gravitational wave amplitude, the height of the wave. The further away the merger, the smaller the amplitude. I'll give another example as well. The total mass of the merging binary, the sum of the 2 individual black hole masses, affects how long the gravitational wave signal is. The heavier the system, the faster it will merge. So the shorter the gravitational wave signal lasts in time. In this equation, I've listed what all these source parameters are that the gravitational wave signal depends on. We can split these parameters into 2 broad groups. The intrinsic parameters, which are intrinsic to the binary itself, and the extrinsic parameters, which describe the location of the binary in the sky, its orientation relative to us as observers, and the time and phase of the binary when it merges. While these extrinsic parameters do affect what a gravitational waveform will look like in our detectors, they're not particularly interesting from an astrophysical point of view, so we tend to factor them out and focus on the intrinsic parameters in our models. But we can simplify even further. While there are waveform models which include the effects of orbital eccentricity, that's how elliptical the binary orbit is, generally we assume that by emitting gravitational waves, this tends to circularize the binary's orbit. So we will assume that there's no eccentricity and E is 0. Additionally, the total mass of the binary, the sum of the 2 black hole masses, acts as a scaling factor to the waveform in time, as we've seen before. So we don't need to explicitly include it in our models. Therefore, our models will depend only on the mass ratio of the 2 black holes, Q, and on the 3D spin vectors, which describe how the black holes are rotating on their own axis, one 3D vector for each black hole, shown by these 2 chi vectors. That makes a total of 7 dimensions. You will probably be wondering, how do all these facts about gravitational waves and binary black holes relate to precession? Well, the answer is that in a merging binary black hole, the 2 objects are spinning in towards each other, and so this rotation can change over time, and binary black holes can undergo precession. This precession will change how the gravitational waves will look. Because black holes are a consequence of relativity, we need to consider precession as described by Einstein's theory of general relativity. There are actually 2 kinds of general relativistic precession effect. The first is called geodetic or de Sitter precession. This kind of precession is due to curvature of spacetime near large masses. It is this kind of precession effect which is responsible for the general relativistic correction to the perihelion precession of the planet Mercury. The second type of general relativistic precession is Lense-Thirring or spin precession. This precession effect is due to frame dragging of spacetime near large rotating bodies. So the difference between this effect and geodetic precession is that geodetic precession happens around any large enough body, whereas for Lenser-Thirring precession, the large body has to be rotating. It is Lenser-Thirring precession which is the more important effect when considering spinning binary black holes. So from now on, whenever I mention precession, I will only be talking about Lenser-Thirring precession. I'm now going to play you two videos side by side of two different binary black hole mergers. In both cases, you can see the binary configuration above and the gravitational wave signal underneath. The purple arrow in both videos represents the orbital angular momentum vector of the system, L, while the mustard and green arrows represent the spin angular momentum vectors of the black holes. In the top left of each video, you can see the mass ratio Q and spin vector components. I'll note before we start that each of these two binary configurations has a mass ratio of 2. So any differences we can see between the systems will be as a result of the spins on the left-hand side initially being aligned with the orbital angular momentum and the spins on the right-hand side not being aligned. You can see that the yellow and green arrows on the left-hand side are either pointing straight up or down, and the arrows on the right-hand side are pointing in completely different directions to the purple arrow L. I'd like you to watch the two videos closely, paying particular attention to any differences you can see between the two. So let's spot the difference. And I wonder how many of these differences you saw. I'll start the videos again. The first difference to note is that on the right-hand side, the direction of the orbital angular momentum is changing as a function of time, whereas on the left-hand side, it is not, it stays fixed. Another difference, on the right-hand side, the two spins are also changing in direction. If this isn't particularly clear from watching the arrows, it is very clear from watching the vector components at the top because they're clearly changing. Whereas on the left-hand side, the spin vectors remain fixed. One final difference, which I'll be really impressed if you spotted, is in the gravitational wave signals at the bottom. On the left-hand side, there is a constant phase difference between the two polarizations. That means there's a constant gap between the red and blue lines throughout the entirety of the inspiral. And the amplitude, the height of the wave, is constantly increasing. We call this monotonic increasing. On the right-hand side, however, there are phase and amplitude modulations. So the phase, the gap between the red and blue, changes. For example, here you can clearly see a gap between the two, whereas here they're on top of each other. And the amplitude, the height, is not increasing all the time monotonically, but it is, for example, increasing here and then decreasing and then increasing again. So neither of the things from the left-hand side are true on the right. The differences that we've just spotted are the effects of precession. Precession occurs in binary black holes when one or both of the spin vectors is misaligned with the orbital angular momentum L. If we imagine that the black holes trace out circles as they orbit each other, in a non-precessing or spin-aligned system, these circles would be restricted to a fixed, flat, 2D plane perpendicular to the orbital angular momentum, called the orbital plane, shown here by the dark blue disk. However, in a precessing system, the orbital plane tilts in time and is no longer fixed. The direction of the orbital angular momentum, as well as the two spin vectors, become time-dependent. We can think of the precession of binary black holes a bit like this gyroscope. The yellow wheel in the middle is the orbital plane, in which the two black holes are rotating around each other and spiraling in towards merger. The axis going through the yellow wheel is like the orbital angular momentum, and this is tracing out a cone shape in space as the system processes. Whereas a system which is not processing is more like this spinning top. The orbital plane is the disk in the middle, and it stays level while the top is spinning. And the orbital angular momentum, this handle, stays pointing upwards. On this next slide, we can see a processing binary configuration again, but this time expressed using the dimensional spin vectors denoted by these S's. The only difference between these S vectors and the chi spin vectors that we saw before is that the S vectors have a factor of the mass of the black hole squared, shown by this equation. At any time during the in-spiral, we can split each of the spin vectors into a 2D part, which lies within the orbital plane, and a single component parallel to the orbital angular momentum L. It is the 4 components perpendicular to L in the orbital plane which source the precession. Therefore, a precessing waveform is dependent upon the mass ratio, Q, the 4 in-plane spin components, and 2 out-of-plane spin components, which makes a total of 7 dimensions. Whereas a spin-aligned waveform is only dependent upon the mass ratio Q and the spin components parallel to L, which is only 3 components. Looking at the diagram, we can see the total angular momentum J as the vector sum of the orbital angular momentum L and the spin vectors, the S's. The direction of J remains approximately fixed throughout the in-spiral, and L precesses around J, tracing out a cone shape which gradually widens and has an opening angle which we call this lambda L. To give you an idea of what the difference between precessing and non-precessing gravitational waveforms looks like, we have a non-precessing system on the left and a precessing binary on the right. We can imagine that the orbital angular momentum L is pointing straight out of the screen. For the non-precessing binary, we can see that the amplitude is always increasing and only the yellow mode is present. But for the precessing binary, we can see excited higher order modes shown by the blue wiggles with amplitudes that are being modulated. For example, look at how the height of this blue mode is changing over time and not always increasing, it goes down here. If you look very closely, you can also see the amplitude of the yellow mode is modulating slightly, although I would be impressed if your eyes can see that. Now that we know what precession is, we ask, why is it difficult to include it as part of our waveform models? The answer is because it introduces complications and breaks all the symmetries which can be used to simplify the modeling of non-precessing systems, such as introducing amplitude and phase modulations, as we saw in the slide before, having to model all 6 spin components rather than just the 2 parallel to L, exciting higher order modes, shown by those blue wiggles in the previous slide. But precession gives us a lot of information about the behavior of the system, which we can use to unlock its secrets. For example, precession is able to give us hints about exactly how the black hole binary might have formed, which in turn gives us information about the environment it formed in. We'll consider 2 ways in which binary black holes could have formed, called formation channels. Consider the panel on the left-hand side first. This is called the isolated binary formation channel, and it starts at the top with 2 main sequence stars in a binary orbiting each other. Each of these stars then dies to form a black hole, and there is a possibility that they end up as a binary of black holes, which will then eventually merge, producing gravitational waves. In this scenario, because they formed within the same binary, the 2 black holes are very likely to be formed with their spins aligned to the orbital angular momentum, so not precessing. However, now consider the panel on the right, which describes the dynamical binary formation channel. Again, we start off with 2 main sequence stars orbiting each other in a binary, and one of them dies to form a black hole. However, the big difference this time is that the binary comes close to another black hole, a third body, where and a dynamical exchange takes place where the main sequence star is knocked out of the binary and replaced with the second black hole. Now, the two black holes have not formed together, so they are much more likely to have spins which are not aligned with the orbital angular momentum, and so produce a precessing gravitational wave. Because the dynamical exchange is much more likely to happen in a dense environment like a globular cluster, we can guess that if we detect a precessing gravitational wave, it came from a binary which formed via the dynamical binary formation channel as opposed to the isolated formation channel. But this is not the only information we can gain from precession. We said earlier that we deduce the parameters of a gravitational wave source by comparing the signal to a bank of waveforms with known parameters. So we guess that this signal has the same parameters as whichever waveform best matches it. However, this process is not always easy due to parameter degeneracies. Here is an example taken from a real gravitational wave detection. First, consider this blue banana in the graph. We are looking at the results for two parameters, the distance to the source on the y-axis and the tilt of the orbital plane relative to us as observers on the x-axis. And anything inside this blue banana is a possible value for our source. In the blue banana, we can see a degeneracy between these two parameters because we aren't sure what the value is for either of them. The orbital plane could be less tilted, as shown by the bit in the middle, and the binary could be closer to us because the distance is smaller. Or the binary could be more tilted at either end, and the binary could be further away. We say that there is a parameter degeneracy between these two parameters. But now consider the solid yellow blob in the middle, which is taking precession into account. Now, we don't have that degenerate parameter shape, that banana, and we know our system is moderately tilted because theta Jn is at about pi/4, and the distance is probably about 750 megaparsecs away. Therefore, by including precession in our models, we have gained a lot of valuable insight about our merging binary and cracked the code of the degenerate parameters. In summary, precession in astronomy refers to the slow change in an object's rotation. Information about a gravitational wave source is imprinted onto the gravitational wave signal itself. And to extract that source information, we use a system of comparing signals to banks of pre-computed gravitational waveforms. Precession adds lots of extra complications to a gravitational wave signal, and precessing waveforms are a lot more difficult to model and pre-compute than non-precessing models. But on the flip side, including precession in our models can give us a lot more information about a gravitational wave source, breaking degeneracies between parameters and giving us information about the kind of environment the binary black hole might have formed in. Thank you very much.